Welcome back to Physics 151. Our last topic for the semester is the definition of a new thermodynamic state function, like the internal energy, but it has the name entropy. And what entropy is used for is to find a way to quantify the second law of thermodynamics and to explain what it is that's happening in irreversible processes that makes them irreversible. So, what we're going to do is go back to our discussion of the Carnot cycle. And the Carnot cycle, which we saw happens in a completely reversible manner, the two steps that involve heat transfers have heats that are absorbed and released that are related through this equation that has in it the ratio of the temperature of the low temperature reservoir, the cold temperature, and the high temperature reservoir. So what we can do with this equation, if we cross multiply, is write it as the sum of two terms that both are the Q, the heat absorbed or released, divided by the temperature of the reservoir that either released or absorbed the heat. And those two terms, taking the sign into account correctly, add together to give 0. So imagine that we have a more complicated process that's still reversible. Something where there's not just two steps where heat is absorbed or released, but we could have lots of steps. And so in the process of accounting for all of those heat transfers, we would be able to deduce from the middle equation that the sum of Q over T for all of the different heat transfer processes that go around a closed cycle would be equal to 0. And of course this is only true if all of the processes that make up this closed cycle are reversible. And this suggests that this quantity Q over T might be something special. It might have a special characteristic because in the same way that when we go around a closed cycle on a PV diagram, the internal energy change is equal to 0, maybe there's some other function that we can define that has the same kind of a property, that when you add up all of these terms around a closed cycle, you get 0. And that's the basis for the definition of what we call the entropy. So first of all, imagine that all of those heat transfers are very, very tiny. And of course they're all reversible. And so if they're all very tiny, then instead of a summation, we could imagine calculating an integral, and the little circle on the integral tells us that this is around a closed cycle, so it's a closed loop on a PV diagram, that this quantity dq over t is equal to 0. And so when we find that we've got a term like this dq over t, we're going to give it a special name. We're going to say that for a differential amount of heat transferred at a particular temperature, we can define a change, a differential change in a function s that we will call the entropy. And so if we had a thermodynamic process that begins in state I for initial and ends in state F for the final, then we could add up all of these changes in S, these entropy changes, to get the overall change in entropy for that process, delta S, or S final minus S initial. So it would be this integral of dq over t. Now notice I didn't put a little circle on the integral sign here because the bottom equation applies to any kind of process just that goes between some initial and some final state. When we were referring to this quantity at the top, then we said that around a closed cycle on a PV diagram that the sum of all those terms would be 0. So here is the entropy change for a series for a process that involves a transfer dq at a particular temperature T. So in terms of this new function, the entropy that we have now defined, we can now restate the second law of thermodynamics. And here's what it looks like. In any thermodynamic process that goes from one equilibrium state to another, the entropy of the universe, and here what we mean by the universe is the system plus its environment, so everything that the system is in contact with, that entropy can never decrease. It either remains unchanged, which would have a delta S of 0, or it increases. And so in an equation form, here's what we're saying. The change in the entropy of the universe, which is equal to the change in the entropy of the system, perhaps the gas that we're talking about, plus the change in the entropy of its environment, is either greater than or equal to 0. And if it's equal to 0, we say the process is reversible. If it's greater than 0, we say the process is irreversible. So here is a quantitative way of summarizing this tendency in nature for certain processes to only go in one direction and not the other. Now, how do I know that this is correct? Well, we can show that this statement is consistent with the second law of thermodynamics, the way that we have applied it to heat engines. So I'll skip over a couple of slides and show you how that works. What we're going to do here is imagine that we had a forbidden process, that we had a hot reservoir, T sub H, and from that hot reservoir, heat was released to an engine, and that engine absorbed the heat and completely converted it into work. So our heat engine statement of the second law of thermodynamics says that you can't do this, that this is impossible. So let's imagine that we have a process like this and see what happens, what the entropy change is. Well, in one complete cycle, right, which is what the engine operates in, the system, which is the working substance of that engine, has a change in entropy of 0, right, because it goes around a closed cycle on the PV diagram. So the environment is just the hot reservoir. That's the only thing that the engine is in contact with, because we're assuming it's absorbing all the heat and converting it all into work. So the environment then has a change in entropy. Going back to the definition of the entropy change, if that hot reservoir has a constant temperature, T sub H, then it's just minus Q sub H over T sub H. And the reason for the minus sign is the hot reservoir, whose entropy change we're calculating, releases that heat, and QH is a positive value. So we put the minus sign in, indicating that from the standpoint of the reservoir, which is the environment, then that heat is a negative term. So the delta S of the universe is equal to the delta S of the system plus the delta S of the environment. We know the delta S of the system is 0. The delta S of the environment is negative QH over TH, and so we get negative QH over TH. What does that mean? Well, we've now calculated the delta S of the universe for this hypothetical process and found that it's negative. And the statement of the second law of thermodynamics in terms of entropy changes would say this indicates that this process is impossible. It never happens in nature. And so you can see that the second law of thermodynamics for heat engines tells us this is impossible. The second law of thermodynamics in terms of entropy change tells us this is impossible because the overall entropy change of the universe would be negative, and that doesn't work. So these two statements of the second law are consistent with one another. And in closing, let's just think a little bit about what this quantity entropy means physically. What does it mean if a system has a high entropy or a low entropy? And to try to illustrate this, let's calculate the delta S of the universe for a very simple process. We've got two objects, one object at a high temperature, another object at a lower temperature, and there's a very small amount of heat transferred from the high temperature object to the low temperature object. Okay, and that's something that we know does happen in nature. So if the amount of the heat transfer is small, let's assume, as a good approximation, that the two reservoirs, the two objects, don't change their temperature. So delta S of the universe would be delta S of the first object plus delta S of the second object, and we're imagining that these two objects are insulated from everything else. So these two objects make up, for the purpose of this calculation, the universe. Well, object number 1 releases heat, so it releases heat Q, so its entropy change is negative Q over TH. Object 2 absorbs heat, so the Q is positive, so its entropy change is Q over TC. And we can see, since TH is greater than TC, the sum of these two terms will be positive. It'll be greater than 0, right? That tells us that this process can happen, because the delta S of the universe has to either be equal to 0 or greater than 0 in order for a process to be permitted, according to the second law. Now, the increase in entropy, that's consistent with the second law, and it tells us not only can this process happen, but it tells us the process is irreversible. If we were to do this calculation over again and imagine heat flowing in the opposite direction, the two signs would be changed, and we would get a delta S of the universe that would be negative, telling us that it wouldn't be possible. Okay? And if we were to continue until these two objects reached a common final temperature, so imagine that the heat that's exchanged is really, really large, then the entropy change would be very large itself, because the entropy change is proportional to that amount of heat, Q. So here's what's happening physically. The kinetic energies of the molecules in the hot object, as these two objects are in contact, those molecules that have the higher kinetic energies are transferring energy to the molecules in the colder object. And so what we would end up with, if we waited long enough, we would end up with the two objects at the same temperature, which would mean their molecules would have a completely homogeneous distribution of molecular energies. In a hot object, the molecular kinetic energies are higher than in a cold object. But if the two objects reach a common final temperature, then on average, their molecular kinetic energies are the same all throughout the new system. So the initial state that had more energetic molecules in one object and less energetic molecules in the other one was, in a sense, very ordered, right? Because the molecules were sorted out so that the high temperature ones, the ones with higher energies, were on one side, and the lower energy ones were on the other side. So that was an ordered system. But as heat transfer takes place and those molecules end up with a more and more even distribution of energies, that produces a less ordered state. And we can say that that final state would be more disordered, because there wouldn't be any obvious hotter or colder object, because their molecular kinetic energies would be distributed quite evenly. So using other terminology, we could say that a state of low entropy is a less probable state than a state of high entropy. So at the most fundamental level, the entropy of a system is a measure of its disorder. The final state has the higher entropy, which is the higher disorder in this example that we were using. And as a result, it's a more probable state. If we wait long enough, that is exactly what we will find is a state where the molecular kinetic energies will be evenly distributed between the two objects. So that's just kind of a very conceptual description of entropy as a measure of disorder. A system with high order, that's a system with low entropy. A system with high disorder, that's a system with high entropy. And so hopefully this helps you understand not just how we calculate entropy, but at least at a very rudimentary level what it means. So hope this helps as an introduction, and I will see you in class.